Hey, section 6.6, operation with algebraic vectors in two space, it's found on page 319. So adding and subtracting vectors into a D when it refers to algebraic vectors is really, really easy. I mean, we just add components, right? For subtracting vectors, we subtract components. Um, so it's following, okay, these two rules, and we often are given vectors in a variety of ways. So I'm going to do this in two methods here. Okay, so how do I find the sum of these two vectors? So the first thing I'm going to do with A is I'm going to change it to components. Okay, and then my question asks me to add the two vectors. So that's really this question. Okay, that's a kind of a weird way to look at it, but what we're asking to do, okay, is this. Okay, add my x's and then add my y components. Okay, and that'll be 3, take away 2 is 1, and negative 5 plus 7 is 2. So that's the resulting vector, okay, 1 and 2. Okay, or I could change B. Okay, a different way to look at it is I could change B to a string of, okay, vectors, or written the way A is written here. That would be a plus 7j. Okay, so A plus B, okay, it is 3i minus 5j plus negative 2i plus 7j. Okay, that's 3i, just collect like terms. Either way is fine. Okay, well, we should be comfortable either way of doing this. You know how to go back and forth between, okay, both methods. Okay, so with vector components, okay, or with unit vector expressions here. And multiplication of vectors, okay, again, is just something we've talked about here, multiplication of vectors here. So given the vector a, negative 2, 1, I'm going to determine, okay, negative 2a, okay, and that's expressed like this. So, as we think, it seems kind of a silly section here, okay, but it is what it is, and it's worth talking about. Okay, so I would have, okay, that's negative 2/3, and then comma 1/3. Find a unit vector parallel to the vector, okay, 3, negative 4. So our unit vector involves finding the magnitude first. Okay, that's going to be 9 and 16. We know that to be 25 or 5. Okay, so my vector, okay, has, okay, a length of 5. So if I divide this vector by a factor of 1 over, okay, I'm just going to call this unit vector. Let's call this a hat, okay? Okay, and then I'm going to multiply it. I'm going to make sure it goes in the same direction, so I'm going to multiply it by the vector. So what this is a hat as a unit vector, okay, and I've got 1/5. Right? I found my magnitude of a is 5, so I'm going to multiply it by a factor of 1/5. And I'm going to make sure that that vector, okay, gets multiplied by that scalar factor of 1/5. Now, if I like, okay, I can leave it in this form, okay, or I can leave it in this form here, okay, or I can actually write it out. Okay, now I haven't done this yet. I'm just going to confirm this since this is a very short lesson here. Okay, so I'm going to confirm that the magnitude, okay, the definition of a unit vector, okay, is that it's 1 unit in length. So I'm going to actually do this calculation. Oh, let's keep. I'm going to actually do this calculation. Okay, so the magnitude of the unit vector a, okay, is going to be 1/5. Oh, sorry, I'm making a few mistakes here. It's not something I've done in a while here, so I'm going to. Okay, so 3/5 and then negative 4/5, quantity squared, and the square root for magnitude. Okay, so what do we have here? Okay, so that's going to be 9/25 25ths, 16 25ths. You notice that that's 25 over 25, or 1, okay, which works out to be unit vector of length 1 here. Okay, so either form is fine. Okay, and this is just, okay, a proof, okay, that a hat is a unit vector, and the definition of a unit vector, okay, is length 1. Okay, pretty straightforward. Very, very easy section, very, very easy applications, and the homework is going to be quite easy to do. Okay, another common application question is the following. Given 3 points that make up a parallelogram, I've got to find the other point, okay, such that it does make a parallelogram. So I'm just going to do a quick sketch here. Hopefully, okay, I'm going to go A, that's negative 2, 3. I'll go across here to B. It really doesn't matter as long as we're consistent. C is going to be my point that I want to try and find. I'm going to call that XY, and then D, I've got 4 and 2. Okay, so I want to prove that this is a parallelogram, and I want to do that by finding what point C, in terms of X and Y, will make this a parallelogram. So I need to find, let's find a couple of things here. Let's find AB. Okay, so I'm starting at A and going to B, so that's going to be negative 1, take away negative 2, and then I've got negative 2 is my Y component of B, take away 3. I've got AB being, okay, that'll be 1 if I get my integers right, so it's a plus, so it's 1, take away negative 5. So this direction vector here has to be identical to this one here, and my direction vector DC, okay, is going to be X minus 4 and Y minus 2. Okay, makes sense? Okay, so now I've got, it was just, sorry, I just paused there checking, okay, my solution here. So I've got this situation, AB equals DC. Okay, so that's going to be the vector 1, negative 5 is equal to X minus 4, Y minus 2. That allows us to solve real quickly 2 systems. I can equate my components. Okay, so 1 is the X component of the vector AB. I'm going to let that equal to the X component, which is X minus 4 of the vector DC, and that's this expression right here. Similarly, I'm going to do negative 5 equals Y minus 2, and I just solve for. Okay, and then solve for Y. Okay, and it looks like that's my point here. So my point C is the point 5, negative 3. Okay, that's easy to do. Just equate vectors and directions, okay, and introduce components here. Okay, and finally one more application question. Find the angle between PQ vectors PQ and vectors PR, where I've given 3 points here. Okay, so let's set this up. Okay, let's call this theta as my angle. So it's going to be between P and Q, okay, and P and R here, where P is 2, 0, Q is 0, 3, and R is the vector, okay, negative 3, 4. All right. I just have 2 vectors and an angle. I think I can easily make this into a triangle, and maybe use the cosine law or trigonometry, depends, some sort of form of trigonometry. So it looks like I'm going to need PR, I'm going to need side lengths, or sorry, PQ, PR is what I need, and PQ over here. Okay, so I need displacement vectors. Okay, so PR is going to be negative 3 take away 2, negative 3 take away 2, Okay, that's negative 5, and negative 4 take away 0. Okay, good, fair enough. Okay, and PQ, my displacement vector is going to be 0 take away 2, that's negative 2. Okay, and 3 take away 0 is 3. And while I'm at it, let's do RQ. Okay, and that'll be 0 take away negative 3, that's 3. And 3 take away 4. So 3 take away negative 4 is 7. Alright, so over here, let's get some lengths here. PR. PR will be negative 5, negative 4. I'm going to do this quickly. Okay, so that's 25. 25 plus 16, that's the square root of 41. Okay. PQ, let's do PQ next. That'll be negative 2 squared plus 3 squared. That's 4 and 9, that's 13. Okay, square root 13. And then RQ is 3 squared and 7 squared. 9 and 49 is 58. If I did my math correctly, I'm just going to check this. Okay, so I've got square root 13, square root 41, and square root 58. Okay, so now I can set up a cosine law. Okay, a cosine law situation on this angle here. Okay, so that's going to be my RQ. That's going to be square root 58 squared. Okay, and then I've got 41 squared plus square root 13 squared minus 2. Okay, multiplied by my two sides times the cosine of theta, whatever that angle is. Okay, and that's the cosine law application. Okay, this is 58, 41 plus 13, and I'm going to work all that out. Okay. Actually, I'm just going to leave the expression. I don't have my calculator with me quite yet. Okay, so I'm going to isolate and solve for cos theta and then do all the mathematical work on my calculator. As is, that'll be 58 minus 41 minus 13, so I'm bringing everything over, and I'm left with bringing the constants over. I didn't say everything quite yet. Bringing the constants over. Okay, so now I can divide by that coefficient of negative 2, square root 13, square root 41, close my bracket, that equals cos theta. Now I can go to my calculator. Okay, when I go to my calculator, I get this ratio here. I'm just going to pause. Okay, so there's decimal approximations. I worked through that and got the following decimals in an inverse cosine division statement. Inverse cosine gave me an angle of 95 degrees. So doesn't quite look like it. It's not, certainly not to scale. The diagram really doesn't matter, but that angle is 95 degrees, and it makes some sense. It's across, that angle's across from the largest side of my triangle here, so it's probably the largest angle in my two vector situation. That's it. That's how we do some of these really quick, fast questions from section 6.6. So have fun, enjoy the homework, and we'll get back to you in another day.